Hello friends, welcome back. In this video we'll be talking about general rotations where we don't have a fixed rotation axis but just rotations in space, and related effects that are a bit more technical and extremely interesting. So we won't go crazy with the mathematical details, but we will mention some of the interesting considerations and consequences of these that sort of are contained under the umbrella term of gyroscopic effects. I'm sure you know what a gyroscope is, or I think you know. If not, you're about to find out in a few minutes. Okay, but let's start with the comparisons that we have between, once again, translational motion and angular motion, to do the following, to build the following intuition. So remember in translational mechanics, when you look at F equals ma, or in general, actually, even without going into dynamics, but just the kinematics of acceleration and velocity, right? When we look at them as vectors, so free acceleration, not on a straight line, and velocity sort of in real three-dimensional space, the general properties of this type of relationship are quite complicated, but we can definitely say at least three sort of simple things that can happen, all right? And one is where the acceleration is directed in exactly the same direction and orientation as v. So if the velocity vector is this one, and you have an acceleration vector that is exactly in the same, actually, let's move all of this. Oops. Let's move this, all of this here. It's fairly easy to realize that in this situation, then the direction of velocity remains the same, and the magnitude, aka the speed, increases. So speeds up. All right. If you're driving your car in a straight line and you push on the acceleration is also, the vector is in the same direction as motion, along, like forward, you will speed up. No big surprise. The second situation is where A is opposite velocity. So same direction, but opposite orientation. And in this case, you know where I'm going. V doesn't change direction. There's no sort of pull in any other direction than the direction of motion, but the speed decreases. So it's slowing down, okay? I think I need to zoom out a little bit. Yebo. The third possibility that we consider is that the acceleration is perpendicular to velocity. So in particular, we would have v like this, and acceleration is, for example, like this. Do you remember when we talked about a situation like this? I'll give you a second, but I'm sure you do. This was as in uniform circular motion. This was one of the examples where this was precisely the situation, where this acceleration here is centripetal. Right? Now, what happens to v in that case? we actually had a constant speed and the direction, obviously, the direction changes. The direction how does the direction change? In the same direction as acceleration. So for example, in this, let me draw it again up here. If velocity is horizontal, but your acceleration is vertical, then one moment after that, your velocity will be pointing slightly upwards in the same direction. So the change of velocity is obviously parallel to acceleration. That's the whole point of acceleration. Now, why did I spend so long talking about, or things that you know very well already and that have nothing to do with the rotations? Because we have, let me zoom out, or rather, let me clear the page. We have the same exact situation for torque and angular momentum. So we said all of these things of acceleration and velocity, and the relationship between acceleration and velocity is just a derivative. Well, we just discovered, or you just learned, that torque, net torque specifically, and angular momentum are related by the same exact type of relationship than acceleration and velocity. So in the general case where the vectors are oriented whatever of torque and angular momentum, we can still say something simple in three main cases. One is where tau is along the existing angular momentum, same direction, same orientation. And the analogy with acceleration velocity was when acceleration is in the same direction as velocity. Well, we said that the direction doesn't change and that the magnitude increases, so the rotation speeds up. Nice. So if you apply a torque in the same direction as the angular momentum, and remember both are those weird cross products, so for a disk spinning anti-clockwise like this, the angular momentum vector will be pointing upwards. In order to apply a torque that is also upwards, so in the same direction as the angular momentum, you would need, for instance, to apply, let's draw it in purple, a force that is tangential and sort of in the same direction as the rotation. See if you can do it applying the right-hand rule. You would find that with this being the lever arm and that being the force vector, actually let's draw the lever arm in a different color, like this. Your torque is exactly up, and so in the same direction and orientation as the angular momentum, the rotation speeds up and it doesn't change direction. Wonderful. Second case is where tau is opposite to the angular momentum, and you already know what I'm about to say. Same direction, and the magnitude decreases, so the rotation slows down. Very nice. And that would be the case if the force up here is directed in the opposite, still tangential, but in the opposite direction. And thirdly, another situation is where the torque is perpendicular to the angular momentum vector. And in this case, with perfect analogy with centripetal acceleration for linear motion, what we have is that the speed, angular speed in this case, or rather the magnitude of the angular momentum, is constant. So it spins essentially at the same rate as before, but the direction changes. And in particular, the direction changes in the same direction as torque. And that is, again, that's the whole point of torque, to change angular momentum. So it's a little easier, I think, now to start building intuition as to what happens to an object that is freely spinning, so with a certain angular momentum, or a system, not necessarily an object, but a system of objects that are spinning and have an angular momentum. If I apply a torque directed arbitrarily to this system, then the overall effect, actually this is worth writing down, so I'm going to zoom out. So by virtue of what we just said, a most general case of a certain angular momentum and a certain torque applied to it will be a combination of 1, 2, and 3. Or typically either, more precisely, 1 or 2 and 3. Because 1 and 2 are incompatible. Either it's in the same direction or in the opposite direction, can be both. And then the perpendicular component. So whenever you have a certain angular momentum vector and there's a torque applied in a generic direction, then as usual, we can always split this torque into a parallel component to the angular momentum and into a perpendicular component. The parallel component, let's change color. The parallel component, this is cases 1 or 2. In this case is in the same direction as L, so it's number 1, so it determines a speeding up of the rotation. The perpendicular component is, so case 1. This would be case 3, perpendicular. So no speeding up is related to this, is due to this torque, but a change in the rotation axis is, in particular, in the same direction, towards the same direction as the torque. Wonderful. As a famous application, in fact, we'll be talking about the gyroscope precisely now. So in its simplest manifestation, a gyroscope is basically like a shaft and an object, let's say a disc or a wheel, that is able to spin about this point. My arrow is not the prettiest thing. Okay. And free to move to also, and we'll see why it's relevant to move in this sense. So for this axle here to rotate. Now, if this is spinning, so it has a certain moment of inertia, it has a certain angular velocity, and in particular for this type of rotation that I drew on the board, the angular momentum, see if you can figure this out, and the angular velocity would be pointing out of that wheel radially, okay? And so that is the direction of the angular momentum, and we can look at what is the effect of any torques that are happening. There might be some sort of tensions along this shaft, but that's they apply zero torque because they're along the rotation axis. However, gravity, so the weight, does definitely apply a torque when it comes to this this point, right? There's no doubt about that. And in particular, what is the torque given from gravity? If I imagine that this is, just for simplicity, let's say that it's at a right angle, then this torque is simply the mass of the object times g times the length of the lever arm. Let's call it L, or maybe let's call it R. mgr. Now, how is this torque directed? You can use your right-hand rule skills to say that this is the lever arm vector. Let's draw it here to sort of remove all the noise. This is the force. Then your torque will be going into the page, right? Or into the screen, rather, if you're looking on a screen, which this being a video is very likely that you are. So torque is going into the page, and it's perpendicular to the angular momentum vector. Remember what happened when a torque is applied that is perpendicular to angular momentum? Then same rotation rate, so same angular velocity, and a change in direction. And in particular, a change in direction towards the applied torque, so something like this. And so, much like I drew here, the gyroscope, all of it rotates about this axis. So the wheel does sort of a circumnavigation of the central axle and then comes back, etc., etc., etc. This movement, due to the torque applied, is called precession of the gyroscope. And it's a super interesting phenomenon. By the way, if you really, if you think about it, imagine that this wheel wasn't spinning. Gravity would simply determine that this wheel sort of tips forward and down and falls. And it's not a particularly interesting or mysterious phenomenon. However, if the wheel is spinning fast, that is not allowed by the conservation of angular momentum, and instead of tipping down, what's going to happen is that the wheel stays horizontal and instead gradually sort of orbits around this central axis. How absolutely interesting is that? It's really, really cool. And I will spare you the calculation that take you there, but you can look at the PDF on the module to find the precise, or your favorite textbook obviously also has this explained very well. If you look at the situation from above, you would basically see, so this is the spinning wheel, and this is the shaft, so this is spinning, and you would see it gradually sort of turn around. And let's call phi this angle, you would find that the precession rate, namely the rate of change of this angle here, let's call it big omega, and this is none other than the torque divided by I times the spin rate of the wheel or the disc of the gyroscope. Okay. So this omega is how quickly the wheel is spinning, and instead this, I meant this here, this omega is how quickly the wheel is, the whole gyroscope is rotating, precession about its axis. Okay. And wonderfully enough, this is the same result even if the gyroscope, instead of being at 90 degrees, was at an arbitrary angle theta here. You would still get the same result. And please check out the demonstration of this, because it's an interesting piece of derivation, but a bit too long to do, and also requiring a bit of a careful drawing, which I'm not necessarily exactly known for. Last but not least, just to conclude, there's an additional effect to precession, which is the following. So let me clear the page. Then let's take for specifically this example that I just drew and stupidly deleted now, of the gyroscope, which is initially at a certain angle. So with, let's say, angular momentum that is like this. The force of gravity is pointing down. Torque is pointing sort of, well, formally into the page, but so inducing this type of precession. And if you look at the direction of the angular momentum, so let's strip this down to its sort of bare minimum physical description, then what you'd find is that the direction of the angular momentum would rotate about this sort of cone or this circle up at the top as a result of the applied torque. Okay. If you look closely, it turns out that for physical, so this applies to like a spinning top, for example. If you spin a top on the table, you will see that the rotation axis actually turns around, like moves and rotates, and then comes back to where it started, etc. And if you look even closer, you would find that not only does the angular momentum do this type of motion, but there's a wobble about this arc that the angular momentum sort of follows. And this wobble, in quotation marks, is called nutation. And without going into too much crazy detail, nutation is due to the fact that, well, for starters, we haven't included the angular momentum of this precession of the gyroscope into consideration for how the torque changes the total angular momentum. And we haven't considered that when you first spin a top, an actual physical top or any object, then it won't be, in general, immediately it's not precessing yet. So when, in the very first instant, before precession is kickstarted by gravity, by a torque applied, then there's going to be a tipping, like we discussed for a non-spinning top or gyroscope, and the tipping results in an overshooting of that of this alignment with the precession trajectory, and that overshooting then is sort of offset and brought back to equilibrium, but sort of oscillating around it. Again, I don't want to confuse you more than I already am. I will, however, mention that these are not just interesting mathematical facts. These actually happen in real-life gyroscopes and real-life tops. And everybody's favorite spinning object in the universe, or well, one of our favorites, is the Earth. And the Earth experiences both precession and nutation of its rotation axis. Why, you may ask? Because didn't I just say that that gravity from the sun and from the moon is directed along, the lever arm, so it wouldn't apply any torque? Well, it turns out that the Earth is not a perfect sphere, and as a result, there is a small but non-zero torque, and we'll study this in the tutorials, that the sun and moon apply on the Earth, and this is precisely responsible for the precession of the rotation axis of the Earth. And then other effects like the other planets in the solar system, etc., they're also responsible for the nutation. Really interesting stuff. Go and look it up and study more if you're interested. But this was it for now. Thanks for your patience, and thanks so much for watching, and I'll see you soon.